Over the years, I developed an appetite for pure mathematics during my pursuit of theoretical physics. From my own experience, unlike engineering and physics that I need to put my questions on the shelf most of the time, I can go full-on relentless mode in pure mathematics. Although I'm no genius here and I'm pretty slow in learning, this is one subject that I believe I can get solid answer if I'm stubborn enough to dig until the rock bottom. Being annoying and questioning everything is not an option. It is a must, and I'm definitely not up to the professional level yet. With that being said, the following is the text that I'm going to read through with as much care as possible. Let H be a subgroup of G, then H is normal subgroup of its normalizer NH. If K is any subgroup of G containing H and such that H is normal in K, then K is a subset of NH. If K is a subgroup of NH, then KH is a group and H is normal in KH. The normalizer H is the largest subgroup of G in which H is normal. One thing I love about mathematics is its logical flow. There's not much referring to other texts or we'll come back to this later type of sentence in mathematics, making mathematics an easy to follow reading material if given enough caution to the intricacies of the arguments. Let's take a look at the first two sentences. Let H be a subgroup of G, then H is a normal subgroup of its normalizer NH. First of all, the normalizer NH is a set of all elements X in G such that XH X inverse equals H. In order for H to be a normal subgroup of NH, NH must be a group in the first place. Since the associativity property and the unit elements are directly inherited from G, and the inverse elements are directly involved in the definition, only the closure of the law of composition needs to be verified. Assuming both X and Y are in NH, this means that XH X inverse equals H and YH Y inverse equals H. Since bracket XY bracket Y inverse X inverse equals E equals bracket Y inverse X inverse bracket XY bracket XY H bracket XY inverse equals bracket XY H bracket Y inverse X inverse. Because of associativity, I can further write X bracket Y H Y inverse X inverse equals XH X inverse equals H. Thus, XY is also in NH, and NH is indeed a group. Now going back to H being a normal subgroup of NH, it means for all X in NH, XH X inverse equals H. Because all elements H in H certainly fulfill the condition of HH H inverse equals H, which means H must be included in NH, and by definition of NH that all elements X in NH satisfy XH X inverse equals H, H is a normal subgroup of NH. Next, let's take a look at the third statement. If K is any subgroup of G containing H and such that H is normal in K, then K is a subgroup of NH. By definition, this means that all elements K in K satisfy KH K inverse equals H, which implies that they are also in NH. Thus, K is a subset of NH. For the fourth statement, if K is a subgroup of NH, then KH is a subgroup and H is normal in KH. Let's first check whether KH is a group. Since the law of composition, the associativity property, and the unit elements are inherited from the group G, closure is the property needs to be checked. Let K, K prime be elements in K, and H, H prime be elements of H, then KH and K prime H prime are elements of KH. Since bracket KH bracket K prime H prime equals K bracket HK prime H prime by the associativity property, and K is a subgroup of NH such that for all elements K in K, KH equals HK, which means that for any H in H, there exists H double prime in H such that HK prime equals K prime H double prime. Then K bracket HK prime H prime can be written as K bracket K prime H double prime H prime. Applying associativity again, we get bracket K, K prime, bracket h double prime h prime. In terms of inverse element, for all elements kh in kh, there exists h inverse k inverse such that bracket h inverse k inverse bracket kh equals h inverse bracket k inverse k h equals h inverse e h equals e equals k e k inverse equals k bracket h inverse k inverse equals bracket kh bracket h inverse k inverse. Again, because every k in k normalizes h, which means there exists h prime in h such that h inverse k inverse equals k inverse h prime, which is in kh. Therefore, kh is a group. To verify that h is normal in kh, consider bracket kh h bracket kh inverse. Since bracket kh inverse equals h inverse k inverse, we have bracket kh h bracket h inverse k inverse. Applying the associativity property, we have k bracket h inverse k inverse, which results k inverse equals h. Thus, h is normal in kh is shown. For the final statement, the normalizer of h is the largest subgroup of G in which h is normal. This is also true, because we prove that the third statement is true. Namely, if K is any subgroup of G containing H and such that H is normal in K, then K is a subset of NH. This means that NH contains all subgroups of G in which H is normal, making NH the largest subgroup of G. Thus far, I showed that these statements are true by digging deep enough into each of their definition, which demonstrates that mathematics is more about the discipline of constructing logical arguments in the fundamental level instead of fancy equations flying around the air like most movies portrayed. I hope this type of sharing my own homework is helpful. Thank you for watching, and I'll see you in the next one.